He was the first interstellar visitor ever encountered by humankind. Moving at astonishing speeds, with a mysterious acceleration that defies existing knowledge, he raised the question, was this a miracle of nature or evidence of alien technology? Without a cometary tail, yet somehow accelerating and reflecting light at a rate 10 times greater than typical asteroids or comets, his arrival ignited fierce debate among scientists worldwide. A professor at Harvard even proposed a bold theory. Could this object be an alien probe, or perhaps a light sail? His appearance sent shock waves through the scientific community, sparking heated discussions across the globe. In this video, I will take you through the most recent discoveries about Oumuamua and unravel the many mysteries surrounding it. On October 19, 2017, a telescope at the Haleakala Observatory in Hawaii spotted a rapidly moving point of light. At first, no one paid much attention. After all, the solar system isn't a sealed box. Beyond its distant edges lies the hypothetical Oort cloud, a vast sphere of icy bodies that may stretch far beyond the Kuiper belt. Occasionally, passing stars disturb these outer objects, knocking some of them loose. A few fall inward and become long-period comets visible from Earth. Others are flung outward, cast into the abyss of interstellar space. Similarly, other stellar systems in our galaxy might possess their own comet reservoirs. As stars drift and dance through the Milky Way, their gravitational fields constantly interact, ejecting some objects from their systems and capturing others. Scientists estimate that over 10,000 such small objects may pass through the inner solar system, inside Neptune's orbit, every single day. So when Oumuamua was first spotted, astronomers assumed it was just another long-lost comet from a distant system. It was quickly given a cometary designation, C 2017 U1. But soon, something didn't add up. No matter how carefully astronomers observed, they couldn't detect the faintest trace of a tail or surrounding gas cloud. No coma, no dust. It was a comet with no soul, a truly bizarre anomaly. As a result, in an unprecedented move, it was stripped of its comet status and reclassified as an asteroid, A 2017 U1. This marked the first time in human astronomical history that an object's identity was officially reversed in this way. Yet the surprises didn't stop there. As scientists calculated its trajectory, they collectively gasped. It was traveling too fast. Its speed was sufficient to escape the sun's gravitational pull entirely, following a hyperbolic trajectory through the solar system, never to return. This irrefutable data proved that Oumuamua was not native to our solar system. It was a true interstellar traveler. To commemorate this historic discovery, the object was named Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. The International Astronomical Union quickly established a new classification just for such bodies, the I designation for interstellar. Thus, Oumuamua became the very first official member of a new class of objects, I 2017 U1. With this, humanity's understanding of the universe quietly turned a new page. But no one expected the first interstellar object to be so strange. From its shape to its motion, everything about Oumuamua defied explanation. Mystery number 1. What does it actually look like? It's tiny, between 100 meters and 1 kilometer long, but its shape is wildly unusual. Based on its dramatic brightness fluctuations over a 7-hour rotation period, scientists inferred that it was either shaped like an elongated cigar, possibly with a length-to-width ratio of 10:1, or like a remarkably thin disc or pancake. Either form exceeds the limits of what's considered natural for most space objects. Even stranger, it wasn't rotating in a stable fashion. Instead, it tumbled erratically through space like a spinning top knocked off balance. Awkward, chaotic, and uncontrolled. Mystery number 2. Where did it come from? If Oumuamua is asteroid-like, it would suggest formation near a star's habitable zone. But how could it have been ejected so violently across the galaxy to end up here? Was it the result of a cataclysmic planetary collision, or debris from a massive system-wide cleanout? If, on the other hand, it was truly a comet cloaked in dust to disguise its icy nature, then how long had it been drifting in the cold interstellar void? Millions of years? Billions? Mystery number 3, and the most confounding of all, its ghostly acceleration. This became the central puzzle surrounding Oumuamua. In September 2017, it swept past the Sun at a staggering velocity of 87 kilometers per second. Yet unlike any known asteroid or comet, it inexplicably accelerated as it left the Sun, without releasing any visible gases or tail. That baffling behavior became the strongest argument for a possible artificial origin, or at least for unknown physical mechanisms at play. According to the law of universal gravitation, any object moving away from the Sun should gradually slow down due to the Sun's pull. But observational data told a different story. Oumuamua's deceleration was far less than expected. It was as if some mysterious, subtle but persistent force was gently pushing it from behind, partially offsetting the Sun's gravitational tug. This non-gravitational acceleration, though slight, around 17 meters per second squared near the Sun, was undeniably real and could not be explained by gravity alone. And where there is acceleration, there must be thrust. But where did that thrust come from? Another mystery was its unusual brightness. Initially assumed to be a dull, rocky object, further infrared observations from the Spitzer Space Telescope and others revealed a startling truth. Oumuamua was unusually reflective, at least 10 times more reflective than typical comets or asteroids in our solar system. It gleamed like polished metal. Now we had an object with a bizarre shape, an unknown origin, extreme brightness, and the ability to accelerate with no observable means of propulsion. These features combined to make Oumuamua profoundly different, almost eerily so. The scientific community was ignited, theories clashed, ideas collided, and the debate burned brightly. Facing the unexplained acceleration, scientists stretched their imaginations. Could it be caused by solar wind or radiation pressure? Calculations showed that for an object of Oumuamua's size, such forces were far too weak to account for the observed speed change. What about comet-like outgassing? Yet every observation confirmed there were no visible jets, no dust, no gas, nothing at all. With the data refusing to cooperate, the scientific world split into two main camps, and a captivating debate took shape. Camp 1, challenging convention, proposing alien technology. Leading this charge was Harvard astrophysicist Avi Loeb. He made a bold assertion. The simplest explanation for Oumuamua's behavior might be that it was not a natural object at all. He calculated that if the object were extremely thin, just a fraction of a millimeter thick, like a piece of paper, then the pressure of sunlight alone could produce the observed acceleration. But such a razor-thin structure is virtually impossible to form naturally. Based on this, Loeb proposed that Oumuamua might be a light sail probe built by an alien civilization, designed to travel between stars, propelled by the gentle push of starlight. Perhaps, he argued, we had just happened to catch it as it passed briefly through our solar system. This hypothesis was electrifying and instantly captured the attention of global media and the public alike. Camp 2, seeking natural explanations within known physics. Not all scientists were convinced by the alien hypothesis. A team led by Cornell University's Daryl Seligman and others took a different approach. They initially proposed the hydrogen iceberg model, theorizing that Oumuamua was composed mainly of solid hydrogen. At extremely low temperatures, hydrogen can freeze and later sublimate into invisible gas. Thus, as the object neared the Sun and warmed up, hydrogen outgassing could provide thrust without producing visible signs like dust or vapor. It sounded promising, but Avi Loeb quickly countered, solid hydrogen is too unstable. Even the faint starlight during a long interstellar voyage would gradually heat and vaporize it. A hydrogen iceberg, he argued, could never survive the journey intact. Refusing to back down, Seligman's team refined their theory. Collaborating with Jennifer Bergner at the University of California, they proposed a more nuanced comet model. In this version, Oumuamua was primarily composed of familiar water ice, but over its long interstellar journey, it had absorbed and trapped a significant amount of molecular hydrogen, acting like a sponge. This idea is both theoretically and experimentally plausible, as cosmic radiation in space can enhance this hydrogen trapping process. When Oumuamua approached the Sun, the warming caused changes in the ice's crystal structure, slowly and steadily releasing the trapped hydrogen gas. This outgassing, though gentle and invisible, could provide the necessary push without releasing any dust, and thus without producing a visible tail. Based on this mechanism, the team proposed a new class of celestial body, the dark comet. These are objects that accelerate due to the release of internal crumthane, invisible gases like hydrogen, yet show no traditional signs of cometary activity. No coma, no tail, no jets. This intense scientific debate over the true nature of Oumuamua became a battleground of ideas. Loeb maintained that even this refined comet model contained mathematical and physical inconsistencies, continuing to champion his alien light sail theory. Then came a surprising twist. Seligman's team began to wonder if their dark comet theory was correct. Could such objects exist not just in interstellar space, but also within our own solar system? They scoured existing asteroid data, focusing on objects with slightly anomalous orbits, those that appeared to experience unexplained, non-gravitational accelerations but showed no visible signs of outgassing. And indeed, they found a few. A total of 6 small asteroids were found to perfectly match the characteristics predicted by the dark comet theory. All of them are very small and appear utterly ordinary at first glance. For a long time, their extremely faint accelerations had been dismissed as observational errors or unexplained anomalies. But this new discovery was monumental. It suggested that the kind of invisible thrust seen in Oumuamua might not be so rare after all. It could, in fact, be happening right under our noses. This provided strong, indirect support for the dark comet hypothesis. Even more exciting is that one of these 6 suspected dark comets, 1998 KY-26, has already been selected as the next target by Japan's Hayabusa 2 spacecraft. After successfully completing its sample return mission from asteroid Ryugu in 2020, Hayabusa 2 set off on a new journey to pursue 1998 KY-26. It is expected to perform a close flyby of the asteroid around 2031. This mission will offer an unprecedented opportunity to directly observe whether any gas is being released from its surface, potentially confirming or refuting the dark comet model. Such a discovery could become a key breakthrough in unraveling the mystery of Oumuamua. As promising as this mission is, 1998 KY-26 is still not Oumuamua. The original interstellar visitor remains shrouded in unanswered questions, especially regarding its true origin and composition. All we know for certain is that it came from the distant stars. Astronomers traced its trajectory and estimated that it may have originated in the direction of the constellation Libra, even narrowing it down to a few candidate stars. But none could be definitively confirmed. Now, Oumuamua is speeding away at 26 kilometers per second, heading into deeper interstellar space. It has already traveled more than 6 billion kilometers from Earth, beyond even the region where Voyager 1 captured the iconic pale blue dot image. It is far outside the reach of any telescope on Earth. Are we to let these mysteries fade into the darkness along with Oumuamua's vanishing silhouette? Some scientists, unwilling to let go, have proposed an extremely bold idea: to launch a spacecraft and chase after Oumuamua. It sounds like something straight out of a science fiction novel, and the challenges are indeed immense. First is the speed gap. Oumuamua is moving too fast for any of our current rockets to catch up. Second is the deceleration problem. Even if we could match its speed, how could we slow down accurately enough to enter orbit or land on such a fast-moving object? Third is the targeting issue. In the vastness of space, trying to locate and lock onto a small tumbling object just a few hundred meters long and barely visible would be like finding a needle in an interstellar haystack. Despite these staggering challenges, scientific enthusiasm remains undeterred. One project in particular, Project Lyra, has proposed several highly sophisticated pursuit strategies. The core idea behind these proposals is to use gravity assists, just like playing billiards, to slingshot a spacecraft past Earth, Venus, Jupiter, or even the Sun, leveraging their gravitational fields to gain speed or alter trajectory. One of the more viable plans suggests launching a spacecraft in the 2030s. Through a carefully timed series of gravitational assists, the probe would gradually accelerate and shift course, building up enough velocity to reach the fading trail of Oumuamua far beyond the outer solar system. Here's the final part of your narrative, translated into a seamless, coherent English text. If all goes as planned, we may finally catch up to Oumuamua around the year 2048. The mission's designers believe that given Oumuamua's uniqueness and immense scientific value, Such an interstellar pursuit is not a matter of if, but when. Of course, chasing down Oumuamua comes with astronomical costs and considerable risks, which raises the question, do we have other options? Fortunately, the future of astronomical observation is rapidly advancing. The upcoming Vera C. Rubin Observatory will bring unprecedented sky survey capabilities. It's expected to detect dozens, possibly even hundreds, of interstellar objects like Oumuamua each year. More importantly, it will provide months of early warning before these objects arrive, giving scientists precious time to prepare. This will open the door to studying an entire population of interstellar visitors, offering a treasure trove of data that could reshape our understanding of the cosmos. Meanwhile, the European Space Agency's Comet Interceptor mission is taking a different approach. Scheduled for launch in 2029, it will wait in space like a cosmic catcher's mitt. Once a suitable long-period comet, or a new interstellar object, is detected heading into the inner solar system, it can quickly redirect itself to perform a close flyby. Projects like this will undoubtedly revolutionize our understanding of interstellar bodies. But still, none of these missions can replace the study of Oumuamua itself. Each interstellar object may carry unique information from its parent star system. And Oumuamua, being the first one ever discovered, and acting so radically different from anything we've ever seen, might hold secrets that no other object can reveal. If we choose to simply wait for the next Oumuamua, we might get lucky. But the window to unravel this first visitor's mysteries could close forever. So what exactly is Oumuamua? Is it a dark comet, cloaked in a disguise of invisibility? A fragment of an alien light sail drifting silently between the stars? Or is it something entirely new, something that current science cannot yet comprehend? To be honest, until we obtain direct evidence, the scientific community cannot offer a definitive answer. But the pursuit of Oumuamua's truth isn't just about satisfying our curiosity, it's about finding our place in the universe. It's about understanding the origins of life and the grand evolution of the cosmos itself. Whether we choose to send a spacecraft on an interstellar chase, or patiently wait for the next visitor from beyond, the journey will be one of humanity's greatest adventures, a testament to our intelligence, our wonder, and our courage to seek the unknown.